Hello, my name is Nobufusa Kobayashi from Nagoya University, Japan. Here I will talk about an anisotropic dark energy model and its observational constraints. First, let me briefly introduce the standard model of cosmology, the lambda-CDM model. Observations have established that the universe is undergoing accelerated expansion. To explain this, dark energy is introduced. In the lambda-CDM model, dark energy is described by cosmological constant in Einstein's equation. I'm showing this well-known pie chart. About 70% of energy density of the universe comes from the cosmological constant. The model is based on the cosmological principle, which assumes that the universe is homogeneous and isotropic on large scales. Accordingly, we adopt the FLRW metric. Here, the scale factor A does not depend on spatial coordinates, reflecting homogeneity. It also multiplies all spatial directions equally, ensuring isotropy. Despite its simplicity, the lambda-CDM model successfully explains a wide range of observations. However, it is not perfect. With recent high-precision observations, several tensions and possible deviations have been reported. For example, in 2024, the dark energy spectroscopic instrument, so-called DESI, suggests possible deviation from cosmological constant. Their results indicate that the equation of state of dark energy may be dynamical. In addition, some studies have reported possible anisotropy in the cosmic expansion rate. For instance, analysis by Krishnan et al. Suggests that the Hubble parameter may depend on direction. The right panel illustrates such deviations, showing a possible directional dependence of expansion rate. Motivated by these developments, we consider an anisotropic dark energy model based on the Hubble-scale planar domain wall. Let me briefly explain what a domain wall is. We consider a real scalar field with a Zitsu symmetric double well potential. As the universe expands and cools, spontaneous symmetry breaking occurs, leading to a phase transition. Different regions of the universe can settle into different vacuum states. As a result, domain wall forms as topological defects separating these regions. Across the wall, the scalar field moves between the two minima, passing through a higher energy states. Therefore, the domain wall has higher energy density than the surrounding vacuum. Here's an overview of our model. We assume that this single Hubble-scale planar domain wall forms before photon decoupling. We also assume that its effect is sufficiently small at early times, so we start simulation from a homogeneous and anisotropic background. At late times, dark energy, including the domain wall and the cosmological constant, dominates the expansion. In this setup, the domain wall behaves as an anisotropic dark energy component. We numerically solve the evolution equations to study the resulting anisotropic expansion and its observational consequences. We then use observations of the cosmic microwave background, CMB, and type 1a supernovae to constrain the model. We place the domain wall in the YZ direction, like this, so that the X direction is perpendicular to the wall. The spacetime is homogeneous only in the YZ direction, so we can introduce two scale factors, one for X and another for Y and Z direction. The model has two main parameters, d, the thickness of the domain wall, and the tilde omega dW, the potential energy density parameter of the domain wall. Keep in mind that this is not a total energy density parameter. And also, unless otherwise stated, we fix omega lambda is 0.7. Okay, so this slide shows the numerical results of the evolution of the expansion rate. We introduce a parameter to quantify anisotropy. Here, K11 corresponds to the expansion rate in the x direction, while HA var is the mean Hubble parameter. The horizontal x on the right panel represents the spatial coordinate x normalized by the wall thickness, and the vertical axis shows the degree of anisotropy denoted by sigma. We see that anisotropy is significant near the center of the domain wall, but it decreases and approaches zero far from the wall. This means that the universe is anisotropic near the wall, while it becomes effectively isotropic far away. As a result, the region near the domain wall expands faster than the outer region. Okay, because the expansion is anisotropic and inhomogeneous, light propagation is affected. We studied this by solving the geodesic equations. Due to the axial symmetry of the domain wall, we can place the observer along the x-axis and the source in the xy plane without loss of generality. The domain wall lies in the YZ plane, and the observer is located at some distance from its center. In right figure, the axis represents normalized spatial coordinates, and the color indicates the redshift along each light path. The blue dotted line corresponds to redshift z is 1, and for comparing, blue dashed line is perfect circle. The black dashed line represents a straight path. So we can clearly see, right along here, we can clearly see that the light path bends due to the domain wall. We also observe that the lower redshift surface spreads to the y direction. This is because the expansion rate is smaller along the y direction. As a result, photons traveling in that direction experience less redshift. The key point is the observed redshift become direction dependent. As we saw, the domain wall induced anisotropy is redshift. As we saw, the domain wall induced anisotropy in redshift. This suggests that the CMB temperature should also become anisotropic. This panel shows the temperature fluctuations induced by the domain wall. We expand the temperature anisotropy in spherical harmonics to obtain multiple moments. Due to axial symmetry, only the m equals 0 components are non-zero. Using observational constraints from Planck 2018, we can place limits on the model parameters. Here are the results. The left panel shows the case where the domain wall is the dominant dark energy component. The right panel shows the case where the cosmological constant dominates and the domain wall is subdominant. In the left panel, the region below these black lines satisfy the condition for accelerated expansion. However, we found that no parameter region simultaneously satisfy both the CMB constraints and the requirement of accelerated expansion. This indicates that the pure domain wall dark energy model is not viable. In the right panel, all shown parameter regions satisfy the present accelerated expansion. The allowed region satisfy this condition at photon decoupling. Note that we neglect effect between that last scattering surface and the initial time, which introduces an uncertainty of about 20%. Next, we constrain the model using type 1a supernovae data. including Panther Plus, SHOES, and DES Year 5. We perform parameter estimation using Markov chain Monte Carlo method. The upper right panel shows the posterior distribution of tilde omega dw and anisotropic derived parameter sigma. Both parameters are consistent with zero, indicating no strong evidence for the domain wall component. We also compare our model with lambda CDM using the Akaike information criterion and the Bayesian information criterion. In both datasets, the lambda CDM model is preferred over the domain wall model. Okay, so let me summarize. We study a dark energy model based on the Hubble-scale planar domain wall. Near the domain wall, an isotropic accelerated expansion occurs. And this leads to the direction-dependent redshift and affects cosmological observables. Using CMB and Type 1a supernovae data, we found that observations favor the standard lambda CDM model over the domain wall scenario. And for future work, it will be important to relax the assumption of strict planarity and consider more general configurations. It would also be interesting to explore constraints from redshift drift measurements, for example using gravitational waves. Finally, the model should be tested against future, more precise observation of data. Thank you for your attention.